Hello friends, I am Dr. Sudhan Sharma from School of Computer and Information Sciences, Indira Gandhi National Open University. And in our earlier session, we had given you the introduction about vectors, wherein we had discussed about what scalar quantities are, what are vector quantities, what are the important concepts related to the vectors, likewise the magnitude, direction ratios, direction cosines. Apart from this, we also solved some numericals. Now, we are going to extend our discussion for vectors, and in this session you are going to understand about how to perform the algebra of the vectors, likewise performing addition, difference, that is subtractions, multiplication of the vectors, and how to write the vectors in the component form, and what is section formula, and how the section formula is applied into the geometrical problems. So, to begin the session, firstly we need to understand few more concepts. There are co-initial vectors, collinear vectors, and coplanar vectors. So, what are co-initial, collinear, and coplanar vectors? In order to formally understand what are co-initial vectors, the two or more vectors having same initial points. Likewise, over here in this figure, both vectors, say vector A and vector B, are starting from the point O. So, that means both are having the initial point O. So, that is why vector A and vector B are co-initial vectors. Apart from this, in the next figure we are having collinear vectors. And what are collinear vectors? Two or more vectors are said to be collinear if they are parallel in same line, parallel to same line, irrespective of their magnitude and direction. So, if we say we are having this vector and say this is also a vector, then they are parallel to each other and they are collinear. They are lying along the same line, then they are collinear vector. Apart from this, if the vectors are lying into the same plane, say if we are having a plane, say representing say xy plane, and we are having different vectors lying in this plane, say vector A, vector B, vector C and D are lying in this plane, then vector A, B, C, D as shown over here are nothing but the coplanar vectors. So, vectors lying in the same plane are coplanar vectors. That means all vectors will be satisfying the equation of the plane. Collinear vectors are the vectors which are parallel to some line, or they are parallel to one another, and they are the ending point of one is the starting point of the other. Co-initial vectors are those with having the same initial points. So, in order to perform the algebra of vectors, there are some laws, and first law is the triangle law of addition of vectors. Triangle law of addition of vectors, the formal statement says that let A and B be two vectors. Over here A and B are two vectors. We position them so that the initial point of B is the terminal point of A. So, this is the initial point of vector B and this is the terminal point of vector A. So, vector A is this and vector B is this, and vector B, the initial point of vector B is point B and terminal point of vector A is point B. Then vector extending from initial point of A, the initial point of A is this, to the terminal point of B, the terminal point of B is this, is defined by the sum of the vectors. So, say we are having two vectors, this is vector A and this is vector B. So, this is the initial point of vector A, this is the terminal point of vector A, this is the terminal point of vector B, and this is the initial point of vector B and this is the terminal point of vector A. Then the vector from the initial point of vector A to the terminal point of vector B is nothing but vector A plus vector B. So, A is equal to vector AB, A is equal to vector AB. So, AB vector is nothing but A vector, and B vector is nothing but your BC vector. Then AC vector, that is vector AC, will be equal to AB vector plus BC vector. So, I hope you understand that AC vector is nothing but A vector plus B vector, and this is nothing but triangle law of addition of vectors. There is another law of addition of vector which says that, which is parallelogram law of addition of vectors, and it says that if vector A and B are represented by the two adjacent sides of the parallelogram, two adjacent sides of the parallelogram, you need to monitor this. Then their sum A plus B is the vector represented by the diagonal of the parallelogram through their common points. So, this is vector A, say this is vector A and this is vector B. So, this is vector B and they are the two adjacent sides, these two are the adjacent sides of the parallelogram. So, this is vector A and this is vector B. So, if we draw in parallel to vector B, say we draw the vector in the manner, say this is the vector, this dotted line represents the vector parallel to vector B, this is vector A. So, this is vector B itself and this line, this is vector A because having same magnitude and same direction. So, two vectors are equal. So, the vector from the starting point of A and from the terminal point of B by the triangle law of addition of vector will be given by A plus B. On applying the triangle law of addition of vectors onto this triangle also, from the starting point of B to the terminal point of A, again this will be A plus B. So, that means the adjacent sides of the parallelogram are AB, that is AB. So, vector AB represents the one of the side of the parallelogram and vector AD also represents the adjacent side of the parallelogram. So, AB plus BC. So, AB plus BC. AB plus BC is nothing but equal to AC, is nothing but equal to the diagonal term by applying the triangle law. But BC, but you know that BC is equal to AD. You know BC, what is BC? BC is this vector. So, BC is equal to AD because they are parallel to each other. So, that means you can always write that AB plus AD. So, AB, which is direction this, AB plus AD is nothing but AC. So, that means diagonal represents the sum of the vectors A and B. Let me re-explain you. This is vector AB, this is vector AD, this is vector BC and this is vector DC. Now, AB vector is equal to DC vector and AD vector is equal to vector BC. By applying triangle law of addition of vector to vector AB and BC, you can say that AC is equal to AB plus BC. AB plus BC is equal to vector AC by applying triangle law of addition of vector. But you always know that BC is in parallel and is equal to the vector AD. Vector AD. This vector and this vector are same because BC is equal to AD. That means replacing BC by AD in this expression, you can rewrite that AB plus AD is equal to AC. So, AB is this, AD is this as equal to AC. So, AB and AD are actually the adjacent side of the parallelogram. So, the law of parallelogram of addition of vector says that if A and B are representing the two adjacent sides of the parallelogram, then their sum is the vector represented by the diagonal of the parallelogram through common points. So, these two are the laws and now we are going to extend our discussion to the properties of the vector addition, and first property is that vector addition is commutative, and commutative property is that A vector plus B vector is equal to B vector plus A vector. So, by looking at this figure, you can always see that by applying the triangle law of addition of vector, A vector is equal to vector OA and B vector is equal to vector AB. So, OA vector plus AB vector is equal to AB vector is equal to OB vector by triangle law of addition of vector is equal to vector A plus vector B. Similarly, vector because vector AB, this vector AB is parallel to vector OC, so vector is equal to OC vector, and which is our vector B, and OA vector is equal to vector CB, that is vector A, because this is parallel to this vector and this is parallel to this vector. So, applying the triangle law of addition of vectors to the triangle OCB, you can always write it is equal to B plus A. So, this plus this is equal to B plus A, and this plus this is equal to A plus B, which proves that the addition property is commutative in nature. A plus B is equal to B plus A. Similarly, we are having the associative property of addition of vector, which says that A plus B plus C is equal to A plus B plus C. So, in order to understand this property, just have a look at this diagram, wherein vector PQ is equal to vector A, vector QR is equal to vector B, and vector RS is equal to vector C. So, PQ plus QR vector, applying the triangle law of addition of vector to PQ and QR, the resulting vector will be equal to PR, which is A plus B, A vector plus B vector. A plus vector plus B vector is nothing but vector PR vector. Now, that means PR vector plus RS vector is nothing but equal to PS vector. So, PR plus RS, what is RS? Is C. So, you can always write PR vector plus RS vector as A plus B, A vector plus B vector plus C vector is equal to vector PS. So, we got one expression, that is PR plus RS is equal to A plus B plus C, which is left hand side of this equation. Now, let us check it for the right hand side of this expression and try to understand that what is the associative property. So far as the right hand side is concerned, on the right hand side we are having A plus B plus C. So, if we look at vector QR is equal to B and RS vector is equal to C, then applying the triangle law of addition of vector to this vector, that is QR and RS, the resulting vector will be B plus C. So, B plus C is nothing but vector QS. So, QS vector is equal to QR vector plus RS vector, that is equal to B vector plus C vector. Now, again applying triangle law of addition of vector to the triangle PQS, wherein vector PQ is A, vector A, and QS is nothing but vector B plus C. So, the resulting vector will be PS. So, resulting vector PS will be equal to PQ plus QS, where PQ is vector A and QS is vector B plus vector C. So, in both cases we are having PS as the final solution, and at one point of time we are having A plus B plus C, and while evaluating right hand side we got A plus B plus C, which shows that vectors are associative in nature, that is A plus B plus C is equal to A plus B plus C. So, let us solve some numericals. Say vector A is given to us is 2I plus 3j minus k, and B vector is given to us as I plus 2j plus 3k, and we are supposed to find 2A plus 3B and A minus 2B. So, 2A will be equal to 2 times of 2i plus 3j minus k. So, that means equal to 4i plus 6j minus 2k. So, this is 2a vector, this is 4i plus 6j minus 2k. Similarly, we can calculate 3b vector will be equal to 3 times of I plus 2j plus 3k. That means it equal to 3i plus 6j plus 9k. So, 3i plus 6j plus 9k. So, now performing the addition, that is 2a plus 3b will be equal to, we are going to add the components point wise. So, what was 2a? 4i plus 6j minus 2k. So, and 3b was your 3i plus 6j plus 9k. So, you need to add I component with the I component, j component with the j component, k component with the k component. So, this will turn out to be 4 plus 3 is 7i plus 6 plus 6 is 12j plus 9 minus 2 is 7k. So, I hope you understand that we need to perform addition, subtraction, multiplication, whatever is to be done with the respective directions. Likewise, over here we added the values in the x direction, added the values in the y direction, and added the values in the z direction. I, j, k are representing the unit vectors along x axis, y axis and z axis. I, j, k are the unit vectors along x, y and z axis. So, this is how we solved first question. So, on the same lines you can solve a vector minus 2b vector, and that turns out to be 0 times of unit vector in x axis direction minus j unit vector minus 7 times of k unit vector. Now, another important property for the addition of vectors that we are having a 0 vector, and we learned that 0 vector is a vector whose starting and ending point are same. So, and we learned that in our earlier session that displacement can be a 0 vector, because if say we are moving from point A to point B and the say distance is 10 meter, and we are moving again from point B to point A. So, the displacement is the minimum distance between starting point and ending point, and since the starting and ending point are same, therefore, the displacement can be 0, displacement can be 0. So, 0 vector is actually an additive identity. Additive identity means a vector which is when added to any other vector, then it remains same. So, 0 vector plus a vector is equal to a vector, and this is very much used when we are going to prove some of the identities we will see as the session proceeds. Now, one more important concept is about difference of the vectors. We learned a vector plus b vector, that is the addition of the vectors. But you can always see that it can always be, the difference of the vector can always be represented in the terms of the sum of the vectors. If we can write a plus minus b of the vector b, then it is a vector minus b vector. Then what is minus b vector? Minus b vector is a vector whose direction is opposite from the direction b. I want to say that, say this is vector a, say this is 0 and this is point A, and say this is point B. So, this is a vector and this is b vector, then this vector by triangle of addition of vector will be a vector plus b vector. But if the direction of the vector is changed, if the direction is reversed, so this direction will be say in this direction, then it is minus b vector, because the magnitude is same but the direction is reversed. Now, in this case, by applying triangle law of addition of vector, you can say that this the resulting will be a plus minus b vector. So, this is nothing but a vector minus b vector. So, that means difference is always can always be, or sum can always be represented in terms of the difference, or difference can always be represented in terms of the sum. So, you can also derive the 0 vector by adding negative. That means if say one vector is going in direction A, as we had already discussed in the case of the displacement, say we are having vector A and we reverse the direction, then say this is minus of A, then A vector plus minus of A vector is nothing but a 0 vector, which was the case of the displacement. So, we learned that A minus B can always be represented in the terms of A plus minus B, and the same is expressed over here in this diagram. Over here we are having a vector from A to B, and this is vector A, and we are having a vector B to C, and this is vector, or we can B to C, which is vector B, B to C, which is vector B. So, by applying triangle law of addition of vector, A to C will be vector A plus B. But if we reverse the direction, then we from point B to C, instead we move to the direction B to C dash, B to C dash, then this is vector minus B. So, applying triangle law of addition of vector, you will get the result A C as A minus B. So, we learned that A plus B can be used to understand the concept of the difference of the vector, because if the direction is reversed, then the same vector B can be represented by negative of B, and by applying the triangle law of addition of vector or by adding the vectors, you can determine A minus B. So, that means in this case vector AC represents A minus B, and AC dash represents vector A minus B, and vector AC represents sum of the vectors A and B. Now, there is an important concept, which is the multiplication of the vectors. Say we are having a vector A, then multiplying this vector with, say, some scalar constant lambda, then we are getting a new vector, that is lambda A vector. This concept is similar to the situation when we discussed about the concept of the unit vector. Say I is the unit vector in the direction of, say, x axis, then say this is point 0, this is point 1, 2, 3 and 4. So, if we are talking about this much magnitude of the of vector, then we are talking just about vector I. If we are talking about this much magnitude, then we are talking about 2 times of I. If we are talking about this much, then it is 3 times of I, similarly 4 times of I. So, x values represents x times of I. So, 1, 2, 3, 4 are representing the scalar constants, and I is representing the unit vector. So, you can always multiply any vector with some scalar constant. What I mean to say, not only restricted to the unit vector, say you are having any vector. Likewise, in our previous solution also, we calculated the value for twice of A. So, say a vector A is given to us, and say it is xi plus yj plus zk. Then lambda times of A will be can be written as lambda A vector will be equal to lambda xi plus lambda yj plus lambda zk. Overall, you are multiplying the vector xi plus yj plus zk with the scalar constant lambda, that this is nothing but equal to lambda A. And if we are reversing the direction, then we can have the negative scalar constants also. Likewise, over here, if lambda is equal to minus 1, so A vector is there, and if lambda is equal to minus 1, then minus A is the vector which is reverse in the direction. So, if vector A is going in this direction, then minus A will be going in direction opposite to direction A. So, if we take lambda as a constant whose value is 1 over magnitude of determinant of A, then you can always say lambda into A vector is nothing but A unit vector. Why? Because we learned that any vector is expressed in the terms of the unit vector, and the general expression was A vector is equal to magnitude of A into A unit vector. So, if lambda is taken as a scalar constant of 1 over magnitude of A, then A vector lambda into A vector will always be written as A vector upon magnitude of A. And by looking at this equation, you can always see that A unit vector is equal to A vector upon magnitude of A vector, magnitude of A vector. So, this is nothing but A unit vector. So, you can always say that A unit vector can always be written as A vector divided by magnitude of A vector. So, I hope you understood that by multiplying a scalar constant, you can handle the situation wherein by taking the negative value of the scalar constant, you can represent the vectors which are opposite into the direction. By taking the scalar constant whose value is equal to the inverse of the magnitude of the vector, then you can express the terms in terms of the unit vector also. And you can always see that if A be a vector and lambda 1 and lambda 2 are the scalars, then lambda 1 into lambda 2 of A vector is equal to lambda 1 into lambda 2 of A vector. So, these are the simple identities. I hope you are able to understand them. Now, in order to have better understanding, let us solve some numericals. Over here, we are supposed to find the unit vector in the direction of A vector, which is equal to 3I minus 4k. So, the j component is missing, so we can always express, may express, may not express, it is not a problem. You can always write 3I minus 4k, and then the magnitude of A will always be equal to square root of 3 square plus minus 4 square. That turns out to be square root of 25, and which is nothing but 5. And we always know that A unit vector is nothing but A vector divided by magnitude of A vector, and A vector is nothing but 3I minus 4k, and magnitude is nothing but 5. So, that means splitting the components, 3 by 5 of I unit vector minus 4 by 5 of k unit vector will be nothing but the A unit vector, which is solved over here. Similarly, we are for better understanding one more numerical, find a unit vector in the direction of A minus B vector. So, we are given vector A and we are given vector B. So, we are supposed to find vector A minus B. So, A vector minus B vector will be equal to minus of I plus j plus k unit vectors minus of twice of I unit vector plus j minus 3 times of k. Now, subtracting I component from I component, j component from j component, and k component from k component, you will get minus of 3I plus 4k. So, that means the magnitude of A vector minus B vector will be equal to square root of minus of 3 square plus 4 square. This turns out to be square root of 9 plus 16, that is equal to square root of 25, that is turns out to be 5. So, that means the unit vector in the direction of AB. So, A minus B, the unit vector in the direction of A vector minus B, say let us say this is the representation, will be equal to A vector minus B vector, A vector minus B vector upon magnitude of A vector minus B vector. The magnitude of A vector minus B vector is 5, and A vector minus B vector is nothing but turned out to be 3I plus 4k, which is this value. So, splitting the term, so it is minus 3 by 5I plus 4 by 5k. So, this is the value, this is the unit vector in the direction of A vector minus B vector, where A vector and B vector are given to you. Now, in the beginning of the session, we discussed about the collinear vectors, co-initial vectors and the coplanar vectors, and we extend our discussion of collinear vectors to some more extent. Now, we learned that say this is vector A, and say vector A is from this point to this point, I say vector B is from this point to this point, and B vector is nothing but lambda times of say vector A. And we say A vector is the component form is say given by A1I plus A2j plus A3k. and B vector is given by say B1I plus B2J plus B3K. And from the figure we saw that B vector is nothing but lambda times of A vector. So, B vector is lambda times of A vector. So, that means lambda times of A1I plus lambda times of A2J plus lambda times of A3K unit vector is equal to B vector, where B vector is B1I plus B2J plus B3K. So, comparing the components of the unit vector, you can always say that B1 is equal to lambda A1, B2 is equal to lambda times of A2 and B3 is equal to lambda times of A3. So, and you can always say that lambda is equal to B1 by A1 is equal to B2 by A2 is equal to B3 by A3. So, this is the expression which you had got. So, that means if two vectors are collinear, then the factor by which they are multiplied, the magnitude is multiplied, can always be determined by the ratio of the independent components along x, y and z axis, and that is why this expression holds, that is lambda is equal to B1 by A1 is equal to B2 by A2 is equal to B3 by A3, where B1, B2, B3 are the components of vector B along x, y and z axis, and A1, A2, A3 are the components of vector A along x, y and z axis, and B vectors is lambda times of vector A. So, let us extend our understanding by solving one numerical. So, over here we are supposed to show that 3 points with position vectors 2a plus 3b plus 5c, second a plus 2b plus 3c and 7a minus c are collinear. So, that means firstly let us calculate, say vector A is equal to a plus 2b plus 3c, and vector B is equal to a plus 2b a minus a plus 2b. You can take any vector as a, b or c. Then we can calculate vector AB. AB is equal to b minus a. Always remember vector AB vector is equal to b vector minus a vector, or you can say that if AC vector is equal to C vector minus A vector. If we apply this concept, then we can always say that A vector is equal to say minus 2A vector plus 3B vector plus 5C vector, and B vector is equal to A vector plus 2B vector plus 3C vector, and C vector is equal to 7A minus C vector. Then AB vector will be equal to B vector minus A vector. So, this is equal to A plus 2B vector plus 3C vector minus A vector, that is minus 2A vector plus 3B vector plus 5C vector. Again making the difference from point wise, so subtracting A from A, B from B and C from C, you will get the answer A minus minus 2, that is 3A, and 2B minus 3B, that is minus B. So, and 3C minus 5C, that is minus 2C. So, this is the expression for AB vector which we got. On the same lines, you can get the vector AC is equal to C vector minus A vector. This is our C vector, this is our A vector, and this solves to 9A plus 3B plus 6C, and AB vector is 3A plus minus B minus 2C. So, looking at two vectors, you can always see that AC is nothing but 3 times of vector AB. That means AC and AB are collinear, because vector AC is lambda times of vector AB, which is the important property of the collinearity, that if two vectors are collinear, then one vector is equal to lambda times of the other vector, and we had found that the value of lambda is equal to 3. So, if two vectors are supposed to be collinear, then one vector is to be lambda times of the other vector, and over here we found that vector AC is equal to 3 times of AB vector AB. So, that is why vector AC and AB are collinear, and they are also so this is the thing. Now, we are going to discuss one more property, that is the distributive property of the vectors, and distributive property says that if alpha plus beta are the scalar constants, then alpha plus beta into A can always be expressed as alpha times of A plus beta times of vector A. Similarly, alpha times of vector A plus vector B is equal to alpha times of vector A plus alpha times of vector B. So, these two are the important properties which are represented as a distributed property for vectors. Now, we are going to extend our discussion to understand about the components of the vector. We already learned about the component form of any vector. Say we understood that if say point P, X, Y, Z is any point in 3-dimension space, then vector OP will be represented by Xi plus Yj plus Zk, and this is nothing but the component form of the vector. So, just look at the figure. Say point P is there and the coordinates of point P are x, y, z. So, the line connecting, so the vector connecting from origin is say vector r, and this vector is vector OP. So, this is vector r. So, this vector r can always be represented as xi plus yj plus zk. But how it is represented geometrically, then in that case you need to understand about the geometrical part of this figure. Now, OQ, this is this part and this is nothing but the x axis. So, this is representing xi, that x times of the unit vector I is the unit vector along x axis, and OS is this vector, which is representing y times of the unit vector j is the unit vector along y axis. Similarly, OR is the vector along z axis, and that is why it is represent zk. Now, you can always see that QP1, this is Q, this is point Q and this is point P1, this vector QP1 is parallel to OS, this parallel to vector OS, that is vector Yj. So, that means you can always see that QP is equal to OS, that means equal to Yj. Similarly, QP is equal to OS and P1P is this, and it is always equal to OR. So, that is equal to Zk. So, applying this law of triangle law of addition of vectors, OP, that is vector OP, can always be written as OP1, which is this dotted line, OP1 plus P1P. So, this represents, this is the we had applied the triangle law of addition of vector into this triangle, and we find that vector OP can always be written OP1 vector plus P1P vector. So, this is the representation, but we can always see that OP1, which is this dotted line, OP1 is also equal to OQ plus QP1, OQ plus QP1. Applying this triangle law of addition of vector into this triangle, we can always say that OP1 is nothing but OQ plus QP1. So, replacing this in this equation, you can always see that OP vector can be written as P1P vector plus OQ vector plus QP1 vector, and PP1 vector is nothing but PP1, this vector is nothing but Zk. So, representing QP1, what is QP1? So, QP1 is nothing but Yj, QP1 is nothing but Yj, OQ is this, so this is nothing but Xi, and PP1 is nothing but Zk. So, that means they can be represented in the sum form as xi plus yj plus zk, and which is nothing but the component form of the vector. So, by applying the triangle law of addition of vectors to the different parts of the geometry which is shown to you, you can always determine the component form of a vector, and component form of a vector in two-dimensional space wherein the position of point P is x, y is given by vector xi plus yj. In three-dimensional space, if the coordinates are x, y, z, is given by xi plus yj plus zk. Now, it is the time to understand the section formula. Now, what is a section formula? A section formula is actually a formula which is used to find the position vector of a point which divides the line joining given two points in the ratio m is to n. So, let me explain to you that, say this is the system, say x, y. So, say this is point say P, say this is point Q, and this is some point say x or A, and this points divide the line into the ratio m and n. So, this is say the coordinate of this point are x1, y1, the coordinate of point Q are x2, y2, and coordinates of point A are say x, y. Then you can always understand that, say mapping this figure with this figure, that is figure number 13 shown over here. Say this is origin, so this is origin. So, this is vector B, this is vector A, and this is the vector R who is mapping the point R, which is dividing this line into ratio m is to n. Then this vector R can be derived from the formula m times of B vector plus n times of A vector upon m plus n. So, this is the formula wherein the position vector of the point R is determined by knowing the position vectors of point P and Q, which divides into ratio, this point A divides into the ratio m is to n. So, if there is an internal division, then the section formula is given by mb plus na upon m plus n. But there are situations wherein the division is external. So, in that case we are having the external section formula. In order to understand this, likewise over here we understood this figure. Now, for internal section formula, say this is x y axis, okay, and this is origin. Now, this is vector. This is one vector, say vector A, this is another vector, say vector B, and this is the vector R, which is representing the point which bisects this line, say PQ or AB, where B is x2, y2 and A is x1, y1 into the ratio m is to n. Then the coordinates of the point which is bisecting this line AB in the ratio m is to n will be given by m times of B plus n times of A upon m plus n, which is same over here, m times of B, x2 is component of B and x1 is component of A. X1 is component of A. So, mx2 plus nx1 upon m plus n. Similarly, for y component, my2 plus ny1 upon m plus n, because the coordinates of this are x and y. So, this represents x, this represents y. So, you can always find the coordinates of the point by using the internal section formula, but in the case when there is an external division into the ratio m is to n, then you can understand, say this is the coordinate axis and this is some external point with reference to which we are mapping that this point is relatively, say n units apart from point B and m units apart from point A. So, that means this is the external case wherein, because this point C is not lying between point A and point B. So, this is lying somewhat outside point A and point B. So, in this case external section formula will apply, and by looking up resolving this figure again into the figure which is shown over here, you can always find that the coordinates of this point, that is coordinates of point C, that is x and y, can always be found by this formula, and this formula is nothing but this, that is m times of B minus n times of A upon m minus n, m minus n, it should be m minus n. So, this is m times of B minus n, this will give you the external section formula. So, you can always say this is m times of B minus n times of A upon m minus n, and in the internal formula it is m times of B, this is for internal section, internal, and this is for the external. Now, these are the cases when the point is dividing the vector AB or the line in the ratio m is to n. But if m is equal to n, then in that case OR, applying this formula over here, m is equal to n, say is equal to 1 in the ratio equal interval, say 1 is to 1. So, m is equal to 1 and it is bisecting, it is dividing the line into the equal interval, then it will be 1 into B plus 1 into A upon 1 plus 1, that is equal to A plus B by 2, that is just halving it. So, if this is the midpoint, if R is the midpoint of line PQ, that is m is equal to n, then in that case the vector R will be determined by vector A plus vector B by 2, that is the midpoint. Now, in order to understand this concept, let us solve some numericals. In over here the question is given to you, that is find the position vector of point R which divides the line joining PQ, whose position vectors are 2i plus j minus k, that is these are the position vector of point P, and I plus 2j plus k, this is the position vector of point Q, into the ratio m is to n, that is 2 is to 1. So, m is equal to 2 and n is equal to 1. And we already know now, one correction is there, the sign is minus over here, because in the case of external division the formula will be R vector is equal to m times of B minus n times of A upon m minus n, and in case of internal division it will be R vector will be m times of B vector plus n times of A vector upon m plus n. So, applying these formulas into the given situation, we are given vector P and vector Q as P is I plus 2j, this is Q. So, you are going to write m times of Q plus n times of P upon m plus n. What is P? P is 2i plus j plus k. So, 2i plus j plus k, n is equal to 1, this is P, m is equal to 2 and this is Q. So, upon m plus n, solving by adding the I component, j component, k component separately, you will get that the vector is 4 by 3 I plus 5 by 3 j plus 1 by 3 k. Applying the concept for the external division, applying the formula mb minus na upon m plus n, you can always write it mq minus np upon m minus n. What is m? M is 2, n is 1. So, m is 2, n is 1. P is given to you as 2i plus j minus k and q is given to you as I plus 2j plus k. separating I, j and k component and solving the equation, you will get the answer 3j plus 3k. So, this is the vector for internal division, this is the vector for the external division. There is an important proof which is very interesting, that prove that three medians of a triangle meet at a point called the centroid of the triangle, which divides each of the median in the ratio 2:1. So, just look at this figure. Say we are having a triangle A, B and C, and D, E, F are the midpoints of the triangle, and we are having the lines AD, BE and FC. Then these are the medians of the triangle, and all these three medians meet at a point G. Then this point is called the centroid of the triangle, and this centroid of the triangle divides the medians in the ratio 2:1. 2:1. 2:1. This is to be proved. I hope you understood that we are having a triangle ABC, and we connected the midpoints of each side of the triangle with the opposite vertices, and we are supposed to prove that all these lines are called medians intersect at a point called the centroid of the triangle, and this centroid of the triangle divides these lines into the ratio 2:1. So, let us start. So, let the position vectors of A, B and C be A vector, B vector and C vector. So, for better understanding, say this is our triangle, and this is A, this is B, this is C, and this is our coordinate system x and y. Vector from origin A to this is say vector A, from B to B is say vector B, and to C is vector C. So, these three are the vectors, and D, E, F are the midpoints, and we learned that if internal, in the section formula case, we learned that if it is a midpoint, then the internal section will be A plus B by 2 in this case. The section was MB plus NA by 2 and by M plus N, and if M is equal to N, then it resolves to R is equal to A plus B by 2. This was the corollary which we discussed when we were discussing about the section formula, internal section formula and external section formula. In this case, we understood that point D, E and F are bisecting the respective edges of the triangle ABC into two equal parts. So, that is why the corollary will hold, as a result of which the point D will be having the coordinates B plus C by 2, that is this. Coordinates of this will be A plus C by 2, which is this, and this will be having 1 by 2 A plus B. So, the position vectors of the midpoints D, E and F will be given by B vector plus C vector by 2, C vector plus A vector by 2, A vector plus B vector by 2, where A vector, B vector and C vector are the position vectors for the vertices A, B and C. I hope you understood up to this much. Now, all these vectors are intersecting at one point G. So, let G be the point on the median AD. So, this is the median. Median is the line which is connecting from the vertices to the middle point on the opposite side. So, AD is the median, and it is dividing. We are supposed to prove that it is dividing in the ratio such that AG into GD is equal to 2:1. So, this is AG into DG should be equal to 2:1. Now, this section formula is this G is dividing the line, this point G is dividing the median A into D internally. So, internal division formula should be there, and we are supposed to prove that this division is in the ratio 2:1. So, if we apply this, then OG vector will be equal to 2 times of OD vector plus 1 times of OA vector upon 2 plus 1. We had already applied now that means OD vector was half of B plus C. We derived OD vector is equal to half of B plus C. This was vector for D point. So, this is OD vector is equal to B plus C. So, OD vector is equal to B plus C. So, we can always write that OG vector is equal to 2 times of half of B plus C plus 1 into OA vector is nothing but A vector upon 2 plus 1, that is 3, 2 will cancel by 2 and you will be getting OG vector is equal to A vector plus B vector plus C vector by 3. Similarly, for the other medians BE, BE and FC also, you will find that OG turns out to be A plus B plus C by 3, A plus B plus C by 3. That means all the 3 medians are going to intersect at point G, and which is nothing but the centroid of the triangle. I hope you understood how what is internal section, what is external section, and we had covered very important aspects of the vector algebra in this session. Try to go through the numericals which are solved in this session and apply the concept which you learned in this session into the self-learning material while applying the concepts learned in this session to solve the problems given into your self-learning material. This will give you a better understanding. Thank you.